Okay, good morning, students. Welcome back. I hope you guys managed to solve this example. Before we proceed, I just want to do a quick recap on what we covered in the last lectures for students who probably were not registered at the time. So essentially, what we just covered was the concept of stress. What is stress? So basically, when I explain this is that we have some kind of rod, shaft or bar, and we're loading it up. And as the text says over there, so we have a specimen, we load it up, change of length is induced within the specimen. So obviously, if we apply two loads in different directions, 100 degrees out of phase, we expect a change in length. This change in length causes an increase in length or an extension. And when this happens, we get a corresponding stress and strain induced in the specimen, right? What's important to note of that, again, what stress is defined as is force over area. Its unit is megapascals. Just a brief explanation. Also, it's important to note the stress is acting 90 degrees to the applied force. So an example would be this over here. So it says here when a tensile compressive force is applied to a specimen, a corresponding stress will be induced over an area normal to or at right angles to the line of action of the applied force, and a corresponding strain will be induced along the line of action of the force. So I didn't actually mention that. So the stress is acting perpendicular, strain will be induced exactly in the line of the force. That makes sense. Tensile compressive is essentially the same. So tensile force would be two forces in opposite directions. So we're pulling it, and then compressing will be exactly in the same direction, and then compressing. Okay, so we've done a few examples, just to get a feel of what's exactly what stress is about. I'm not going to go over that. We discussed what strain was, and yes, we did that. Also discussed the concept of the elastic modulus. So it's a very important property. So it's also a way we can, I guess, characterize a material. It's a very important property. And we basically computed it. And then from this, I talked about where, so from this, I linked up to exactly where we get it. Okay, well, I'll just get back to that again. But in this example, we looked at the concept of failure. So we had a rod and we applied a load to it, and then we talked about when would it fail. Because that's what essentially strength of materials is all about, looking at when things will fail. And in fact, also when we design things, we want it to last long, meaning that it won't fail, essentially, in the best way I can put it. Then again, I just showed a table of different elastic moduli over here. So different materials have different elastic modulus, and it means something. Then I basically talked about the tensile test, and this is where we get all those properties we talk about. So, and then I've elucidated upon what is the yield stress, the limit of proportionality, what's the ultimate tensile strength, and of course, and basically when it breaks. So tensile testing machines is how we conduct the test. This is again just talking about that. So we talked about the elastic region, and then we talked about the plastic region. Then also we talked about this is now elaborating on the elastic modulus and where we get it, and the different kinds of materials which have different elastic modulus. And what it actually means is that it's a good case study. Let's say it can be seen that two otherwise identical parts are made of steel and aluminium, respectively. The aluminium part will deform over 3 times as much when subjected to the same load. So this is the way you can understand what an elastic modulus is. Also call it a stiffness of the object, and it will deform less under load. So you could essentially say it's stronger, but it's debatable. Then we just talked about how you can find those properties on the graph. Talked about 2 other parameters within a tensile test, and this is the percentage elongation and the percentage reduction area. these quantified ductility. And I talked about what ductility is. And we've come to this conclusion: a ductile material will exhibit a percentage elongation greater than 5. I always thought it was 20. It's probably because I was told that, then having the research. And then, of course, ductile will be less than 5. Oh, sorry, brittle will be less than 5. Difference between the two. So ductile material is one that can be stretched to form a drawn into a significant degree before fracture. So basically, there's a big plastic range before it breaks, whereas a brittle material only has a little or no plastic deformation in it breaks. So what I'd always say this: ductile material allows us to scream before the boarding collapses, whereas brittle materials, there will be no time to scream, the boarding will just cave in. If in the best possible way I could say in layman's terms. Right, so we did a quick example on that, a tensile test, and then I've had another example in the slides, but you guys can I don't know if you guys would like me to do this example, or can I proceed to today's lecture? That is a very quick recap. So what do you guys like?
Better to do, sir.
Excuse me?
You can do, sir.
So I should do this one, right? The tensile test.
Yeah.
Okay. No problems. So let me just prepare my whiteboard. I have to log in again for some reason. Okay, just give me a minute. Okay, so I'm assuming everyone can see this. I'll just have to, let me just zoom up the picture a bit more. Way bigger, yeah. So we've got a few examples of this in Drotsky as well. And I highly recommend that you actually practice this, because this will definitely come in your tests and exams. It's very important to understand this. All right. So let's attempt this problem. Let's see here. Everything good. So the first part of the question. Okay, let me first read the question. The tensile test was conducted on a mild steel bar. The following data was obtained from the test. The diameter of the steel bar was 3 centimeters. Gauge length of the bar was 20 centimeters. Load at elastic limit 250 kilonewtons. Extension at the load of 150 is 0.21 millimeters. The maximum load was 380. The total extension 60 millimeters. The diameter of the rod at failure was 2.25 centimeters. So they kind of playing around with numbers. I don't normally do this. I normally keep the numbers in millimeters. But anyway, so the first thing is to find the Young's modulus, right? That's going to be A. Start it over here. So what is the Young modulus defined as? Can someone please give a shout? What is the Young modulus defined as?
Sir, Young's model is stress over strain.
Fantastic, fantastic. So it's stress over strain. Now you must bear in mind this is only applicable. So I'm going to sketch a quick tensile graph, tensile test graph over here. Young model is only, it's only this region over here, right? Very important. It's not the ultimate tensile stress, and it's not at fracture, right? So it's very important. So the first thing we have to do now, we have to look. So they're giving us a load here. So the extension at a load of 150 kilonewtons. So we most probably gonna have to, they give the load at the elastic limit. So that's great. So that is just basically at this point here. So that's gonna say it's around 250 kilonewtons. They're also giving you a random load at 150 kilonewtons. And of course, this will correspond to a specific extension of 0.21. So we can actually use that as well. They want the Young's modulus. So what we're gonna have to use here is probably the extension at a load of 150 kilonewtons. You're probably gonna have to use this guy here. For the stress, the elastic limit, I'm just gonna make you aware, this is also called the yield stress. So this particular book calls it the elastic limit, but this is also commonly called the yield stress. So just make you guys aware. Probably shouldn't write in the red with this. Okay, anyway, so let's find let's quickly try and find the Young's modulus. So again, because you're talking about a steel bar, and it'll be very useful for you to know your material properties. So for instance, if you're talking about steel, I'm making a blue here, we're expecting elastic modulus of 200, 210, right? Aluminium around 70, copper around 100. And of course, each material has its own, or each ferrous or non-ferrous metal has its own range. And I'll give you a table, or with that, a more comprehensive table with these properties. Nevertheless, so let's go back. So we're expecting a value around 200. So that's gonna be, that's how we're gonna know if we're correct. So first thing, stress, right? Stress is gonna be force over area. We should all be familiar with this. Our force is gonna be 150 times 10 to the power 3, and this will be, and we're dealing with a cylindrical specimen, so our area was 3 centimeters, and I think that is the thing, maybe, or we can say 3 times 10 to the power negative 2 squared. Then we can get our stress, right? That's the first. Can we get that value, please? And we're using we're using the initial area, and because the shape is still not deformed over here. Well, it's what's in the elastic region, so we normally use the actual diameter of the bar. So can I get this value? This answer should be something megapascals. And I forgot to work it out. And while we're on here, the students on you. Yes.
212,207 megapascals.
Thank you, Gaileen. Thank you, Mr. Silver. Let's just quickly see that. You guys confirm answer? Yes, that looks good. 202.21. Okay, fantastic. We can mute your mic now. We can hear you breathing. Thank you, Pauline. Not 2.12, Lindani. It's something not right there. It can never be that small. That's a very small amount of stress. The next part is to work with your strain. And We've got a change in length of 0.2, so that's extension. That's the change in length, obviously. So that's 0.2 millimeters. And then our initial length was 20 centimeters. So this is going to be 20 times 10 to the power negative 3. And this guy is going to be 20 times 10 to the negative 2. So gauge length of the bar is 20 centimeters. Right? Let's get our strain. I just want to copy something for you here, just to give you a visual. How's my laptop not listening? Okay, so let's just compute the strain in the meanwhile while I'm trying to fight with my laptop over here. There we go. So do we get that strain value? Ah, man, can you bloody believe it? Okay, it's fine, it's fine. I just want to put this here. Is that correct? You guys agree with that? We got that in millimeters, we got that in centimeters. I get a different answer. Why do you get 105? 0.2 millimeters. Should just get 1. And it's unitless. It's meters divided by meters. What do you guys get?
What is that for the change in length? 0.21 or 0.2?
Yes, oh sorry, it's 0.21. Yeah, that's correct.
Okay,
Yeah,
then yeah, then Brett's answer is right.
that's correct. Yes. Yes, sorry about that.
Okay, cool.
You should get 0. Or 1.05 times 10 to the negative 3. Fantastic. So just to give you a graphical or visual representation of what's happening here, I'm busy on a thought was on another blackboard. So you initially have a specimen like this, and then we have a gauge length. And this gauge length in our case was now given to us as 20 centimeters. Or 200 more. Okay, yes, that's perfect. So this is what's happening. And so now it's happening now. We are, oh yes, before we get to that, so I'm just giving you just exactly what's happening here. This is what it looks like. For those who need a picture to see. Okay, just ignore my stuff here. Let me move this way. It's a better way. All right. So to find E, our stress is going to be 212 times 10 to the power 6. And this is going to be 1.05 times 10 to the power negative 3. And of course, over here, we can just divide that. We should get the answer in gigapascals, and we should get 202.105 GPa. So, falls in the range over there was definitely steel. For instance, what I might do in exam or test, and please listen, I might ask you to find G, then I might E, then I might ask which material do you think this is? So I've got these small questions I might throw in just to see if you understand exactly what's happening. Okay, is everyone clear with finding the elastic modulus? Can we move on to B? Yes.
So that means you're not gonna give us this. You said there's a breakdown of what to expect for each material. You're not gonna give us that in the exam. You're just gonna give us a table to understand and have a basis of.
Yeah, I know it depends. I will give a table, but for instance, let me demonstrate this to you. Just give me a second. It's good that you're asking questions. Let me just find this. Let me just find what I'm looking for first. It's just one of those things to just kind of to see if you guys are taking things seriously. Where's my? Just going to my previous folder here. Just give me a second here. There we go. Okay, so I'll show you exactly. This is last year's midterm, and so if you guys do well, I'll share it with you today. Can you guys see it over here? It's gonna share now. Yeah. So Gaileen, for instance, this is what a question might look like. Let me just go full screen here, or let me just zoom a bit further. So I mean, for instance, I'll ask maybe sketch a typical stress and strain graph for an elastic material such as mild steel. So that's fine. I'll say describe the difference between ductile and brittle materials with aid of a sketch and a brief explanation. See there. Select 3 ductile and brittle materials on the materials property table, right? So the table, for instance, will look like that. So if you look at this particular table, what I'm looking for is to understand what's a brittle material and what is a ductile material. For instance, tell me what is a ductile material on this table. I hope you guys can see this. Can students? It's good that she's asking this, so that you guys have an idea of what I might ask. So what is? Give me one brittle material here. Oh man, it's a very bad, very bad copy over here. I can see. I can barely see it. But if you look at this, basically, yeah, cast iron, fantastic. There we go. So if you get cast iron, that's around 4%. That's brittle. So that is one way. I was not going to spend too much time on this particular thing. And what I meant was, you're going to get to table, but what I meant was also, for instance, I ask in this question. No, it's not this one. But yeah, I'm telling you it's a low carbon steel specimen. But sometimes I don't tell you what specimen is. And I ask you here, find the modulus. Then what material do you think it is? Then you will check the table. Then it could be anything. So maybe let's say, for instance, it came out to 70 something. Then you would have known it's aluminium. Did I answer your question?
Yeah, I'm good, thanks.
Okay. So yeah, that's just to make things not so easy. Okay, so we found that. Now we can move on to our what's next here. Our stress at elastic limit, right? So we've got the load at elastic limit, so that's basically your yield stress. I'll denote it sigma y, sigma subscript y, and that's just going to be 250 times 10 to the power 3 power over 4, and we use exactly the same diameter, which was 3 centimeters. Let me square that. So can I get the stress, please? So for this kind of question already, if you're interested, I'll probably give you, depending on the question, this could be 1 mark here, 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 1 mark here. Something along those lines. Or I might just give a mark each for this kind of computation. But it depends on the question paper. Okay, so I normally give a mark for correct substitution and a mark for the answer with the correct unit. If you have the wrong unit, I will not give the mark. So I'm just making you aware. Okay. What do you guys get? What's your yield stress? Yes, Sergio.
353,71 megapascals.
Thank you, Chief. 353.71.
353.71.
Yeah, this looks like a material I've tested before. S355 J R. And the next one. So, guys, what this means practically that if you apply a load any greater than 250 kilonewtons on this thing, it will plastically deform. That means it will not return to its original shape. So we also consider this yield stress a criteria of failure, sometimes depending, normally. So if any stress exceeds this, we deem that the member will fail. And we'll touch on this concept of failure during the course of today's lectures. So C on the percentage elongation, that's fairly easy. Sorry, you can call it percent PE if you want. PE. So here we look at the overall length extension. And remember for this, this is a measure of ductility, right? So we're expecting anything greater than 5% or to be ductile. And of course, this is steel, and steel is considered a ductile material. I'm going to stop a bit, sorry about that. So we've got total extension of 60, and the initial length was 20 centimeters. So we can just say 60 times 10 to negative 3 minus 20 times 10 to the, so the change in length divided by the initial length. So is it 20 divided by negative 2, 20 times 10 to negative 2. Okay, right? So we should get something in percent. This is all the easy stuff. No. What is my initial length? Oh, so it's, this is incorrect on top here. Give me, it should be 20 times 10 to negative 2 minus 60. That initial length was 20, yeah. You get 0.7, so 70%. Put this in context here. Let me just make sense of this. Oh, this initially was 200, the gauge length was 200 millimeters. And extended by 60. So it's 260. Okay, this looks suspect here. This feels suspect. This feels very suspect. Forgive me for this. So let me get this right here. So final length minus the initial length divided by the initial length, right? So the final length is going to be, in this case, if you add up 20 plus 60, so that's a total extension, so that's going to be 200 mole. So that's 20 times 10. We should get 260, so it's 260 millimeters minus 200 over 200. So yeah, I felt victim to these units. And you should get 0.3. Yeah, that looks properly. That looks proper, sorry. So 0.3 or 30%. So remember the total final length. So in a case like this will illustrate, so our initial gauge length here was 20 centimeters or 200 millimeters. You apply the loads and it breaks afterwards, and then we found it as 260. So we're subtracting 260 minus 200 divided by 200. And we should get 30%. All right. Is everyone happy with that? And this is a ductile material. The last one is the percent decrease in area. And here it's just going to be similar to the previous percentage elongation. It's we normally use percentage elongation to anyway check activity. So we're going to say it's going to be the original diameter. So I'm going to say PA maybe, P the percentage reduction in PRA is going to be DI initial squared, DI final squared. Or we can have D1, D2, doesn't really matter. That's going to be DI over here. So initially, and of course, the idea here is the greater reduction area, the more ductile it is. If you think about it, so if we had a specimen, we had two specimens like this. Well, specimen, just do this again. Cut it up like that. Just forgive my poor drawing. And we apply a load, and the more, man, this is not exactly what I'm doing. So let's get it right. And after, and eventually as you pull it, it gets very thin. I know you guys have this definition of not to thin wire. So the thinner it gets, the more ductile. For brittle, for brittle material, it'll just look like this. It'll just break. It won't even reduce in area much. So it'll just have this sudden fracture here. So if you guys get that, so initial diameter, let's have a look at that. It was 3 and then 2.25. So we can just say, I think they're both in centimeters. 3 minus 2.25, 3 squared, 2.25 squared divided by 3. 3 squared, sorry, squared. And you should get 43.75%. Did everyone get that? Is there any questions with the tensile test? This is probably the last time we'll ever do a question like this. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm at 14 mark question. So any questions? Gonna move on. Oh, that's an old end there. Are you guys still there? Mr. Silva? Sergio? Okay, great. So I'd like to move on to where, okay, I'm happy. Fantastic. Thank you. It's good to hear that you're happy. Let's move back to the slide. So that is again, well, we can call this a warm-up, right? I had another warm-up to do actually. Okay, fantastic. Thank you, Ivano. Let's move on. Right. So I think what I'm going to do instead, maybe I'll leave it for later. So I wanted to do this question as a warm-up and see, but I think I'll leave this question for later on in the session maybe. I'll come to it. In fact, I'll leave it as a tutorial, and I want to see if you guys are able to figure it out. It's not that difficult actually. Okay, so let's just move on with the lecture, right? So guys, now I've touched on a tensile test, right? But I'd like to touch on now something relevant to you guys who are marine engineers. Now, I want to show you a standard I was working with during the time what the specific company I was working with. I used to test several materials, specific, not several materials, they may not like several different kinds of steel. And if you would like to have the standards, you can let me know. I've just have a look, and I'm gonna open the standard now. Just give me a second. And this standard was basically the guide on how to design ships, right? And it's ABS standard. I'm sure you guys are aware of this, American Bureau of Shipping. And when you build ships, you have to conform to the standard. Of course, different kinds of standards, but I'm just dealing with the American one for just for the sake of, you get European ones as well. And one, the standard I was looking at, and I'll just quickly share with you. So guys, also my lecture style is that I don't only solely look at the textbook all the time. I try to make it interesting and appealing to you guys, especially marine applications. So you can see that all what we learn here, it's not in isolation. It all comes together. So this is the standard rules, materials, and welding. So this standard basically tells you everything you need to know about when you build a shop, all the testing and all the materials you have to use. So it tells you things like, if you look at on the side there, the materials you need for our construction, right? The equipment needed, materials for machinery, boilers, pressure vessels, and piping. And this is things we touch on, you know. Also welding and fabrication. Also that touches a bit on the NDT here. I was getting with. So just looking at chapter 3 maybe, say materials for boilers, pressure vessels, and piping. So what they talk about here, for instance, is the different grades of material. And I'll quickly show you. So this is for boiler. And I'll just quickly scroll. And they talk about, and I don't know what I'm doing here. I'm just clicking. I'm going to show you. So for instance, if you're dealing with plates grades K, L, M, and N, you've got a tensile strength of 380 to 505. L is different. This is UTS. Grade N has, of course, a high strength. If you look at the yields as well, it increases with K, L, and N. They increase due to the chemical composition. So some of them might have more carbon than the other one. So it's all done essentially through metallurgy, I don't know how other people pronounce it, and of course through the mold. So yeah, basically you can see it over here. So different grades have different chemical composition. Also, if you look at that, so the elongation, and when you normally specify elongation, you specify it over specific length. So as you can see over here, the more strong it gets, the less the less the elongation is. However, it's still considered fairly ductile. So for elongation of 50 mil, so you have a specimen, got a 50 mil length. You can see over here, the elongation. So I'll explain to you how this all comes in together. So this is for boilers, pressure vessels, and piping. The thing I have there, this is for the hull. So when you're constructing the hull, the main body of the ship, you've also got your own grade and stuff. So so you guys get what I just said over there before I move on back into the slide? You get the idea what's happening here. So this standard, I think, yes, it's a episode. How can I help? Hello? Not shy. Okay. So, okay, no worries. So I hope you guys get this. So yeah, this is. I would like to make a textbook or some note where I can actually use the standard and get you guys. Yes, it's important for if you apply for a surveyor, and with being a surveyor, you're gonna have to know a few things. So just to quickly show you how much documents is there. Just quickly see where is it. Oh man, what am I doing here? Just want to share with you. So there's a few of them. See, different parts. And then see there is part 2E. And if I had to look at, for instance, part 1E, okay, that's the condition of classification. It's probably how you classify the ship. If I had to look at the one I'm looking for, I think it's 3E. I'm not sure. It's not 3E. No, yeah, okay. 3E talks about the arrangements of the hull, and what's nice about it, it talks about all these calculations we look at. You know, bending moment and shear force, the wave loads, the bending stress, the shear stress. Ideally, this kind of course or this kind of thing will happen after your training through your diploma. This is directly applicable to you guys. So I hope you guys found it interesting. There's different parts. I don't want to go through all the parts. If you guys would like me to share the standards, please let me know in the comments, YouTube comments, or the chat there. This is another standard as well. So there's a few things. You can have a look at. Okay, let's get back to the slides. So is there any questions on that part? Brent? Ivano? Any questions? Great, Mr. Neto.
No questions, sir.
Okay, great. So just to touch on now again, back to this over here. So here we have different grades, right? So this is for ordinary hull strength steel. So why I'm showing you this is because I might specify this in the test, and I might say I'm using this grade, you know. So you're gonna have to kind of look at the table, and basically this is where you're gonna extract the properties from. So we've got the only strength hull steel, and we've got the high strength hull steel, right? And you have different grades with different properties. Normally it's just defined by tensile strength, it's UTS, it's yield stress, and elongation. That's just basically the point of that. And just to kind of illustrate to you a practical process of what actually happens with this. Let me just go up here again. How it normally works, the material comes from the mold, and once you get the material from the mold, it's manufactured in accordance to a specific standard. Now you get a material certificate. Now I'm going to show you a practical material certificate. Sorry about this. I have to now zoom this up as in the plan anyway. It looks something like that. Probably copy this. I'm just going to create my slide here. I can have it on its own. And as you can see there, it'll tell you, well, it is of a specific coil and is rolled, tells the length of the plate and the width and all of that, the chemical composition. So this gets tested at the mold. And then it'll tell you over here, if you can see over here, you guys see over here, it's mechanical properties. Let me just get another copy. So we have red, and you can see that your yield stress, your tensile stress, your elongation, and HRB is a hardness test. So these properties must conform to that ABS standard. So what normally happens, the surveyor will have a look at the standard. He checks the test and said, oh no, this qualifies to be an ABS grade, A, B, D, E, D, H, whatever purpose. The subsequent step to that is now we get the plate, and the plate goes for construction. And then depending on where the plate is used, it has to go for re-verification at the materials lab, and this is the kind of work I used to do. Quite dirty over there. And I would now prepare specimens again in accordance to ABS. So in ABS again, there are specific things like, let me just show you again, a copy and paste you. I'll tell you exactly where how the specimen must look. So if you look at I'll just show you a standard round specimen. So normally a specimen has to look a specific way. So I gotta make sure that this, I normally give this to machine shop, and the machine shop or in the workshop, they'll machine the specimen out of this plate into something like this. That's conform to the tolerances. And also, I'd like to show you guys, I'll even tell you as far as, I'll show you now, depending on, just trying to find this thing now. Just give me a second. Okay, let me just quickly show you something. Just give me a small second. I'm looking for this. And of course, with these tests, you have to take it at a specific position of the plate. Just can't find the specific thing I'm looking for, or if it's I-beam or L-beam or depending on what it is. I'll take it, it doesn't, okay, fine. And normally we do a few of these. So I have to basically do material verification, retest the steel in accordance to the thing, to be pretty sure that this wasn't they didn't lie. So me surveyor performs a test, and then I, again, so this is a certificate, let me duplicate again, so that we can have it on its own. So I retest, because this is another material certificate, so I retest this, the steel. I make up my own report, I will look at the results, say a few things. The surveyor over here, this is from Pure Veritas, he signs it off, and he says, okay, this is fine, the material conforms to the standard, and then we go back here, and then he says, okay, it's okay to, we can use the material to carry on with construction, because everything is fine. So that is just like a small extra piece I would like to tell you, like how it all fits into the bigger picture. And of course, I'm sure there are other ways. I'm not sure you guys have any experience with material certificates. So, do you guys have any experience with material certificates? Have you guys ever seen it before? Can I just get like a few minutes just to talk about, have you guys ever had experience with material certificates and surveyors in general? Anyone? Please share your experience with us, with myself. I'm really interested to know. Spanje, you got any? Calvin?
Yeah, so material certificates, I've worked with quite a few of them. I just want to put out there, more often than not, you will get the exact same certificate no matter what.
Yeah.
Very often they'll order the stuff in bulk and they will
Mm,
just reuse the certificates. So
yeah.
I specifically like Asymetal.
Yes.
Asymetal does their testings regularly. So
Yes.
theirs is very trustable. However, with suppliers such as Pole Steel, Steel and Pipe for Africa, things like that, they generally get their stock in from China. And
Yeah.
I've actually got quite a few of the exact same certificate. They'll just
Yeah.
reuse it. So sometimes be a little bit skeptical of them. Check the date in particular. That's the most important thing on there. When was that certificate stamped and signed? Otherwise, when you request it, they just send you some old one that they've got on file, and it becomes very hard to trust the material.
You know, for sure. But, that's why, like, like in the case where I work, we have to re-verify and make sure that, we had our own lab
Yeah,
at the Princess to make sure that it is
yeah,
exactly what it is before we actually
yeah,
proceed.
yeah,
Thank you for that.
exactly.
Anything else? Anything else, Calvin? Maybe still there. Great, thank you. Anyone else? Mr. Zuma? Guys, we're just like sharing knowledge over here before I proceed back to the calculations. Anyone else? Sonazo? Yes, Silas. Thank you. Thank you, guys. Yes. I'm listening. Dr. Silva, are you here? Mr. Matasso? Maybe at port, I don't know who's worked at the port, maybe, when new materials are coming in. I guess it's not a relevant question. Tristan, maybe? Okay. Okay, great. Okay, let's finally move on. Let's see. Back to the computations. Okay. Oh yes. Hi, Ms. Paulson. Okay, so next part of this chapter, we're looking at compound members bars subjected to axial loads. Right? Now I've got a very funny example here. But there are two arrangements we're going to be looking at here. One is series and one is parallel. One is parallel, one is series, right? So I'll talk about this. I mean, it's a bit vague here, but on the left swing there are two ropes that carry the weight of the buoy, right? The buoy's weight is shared between two ropes. In this configuration, the ropes are connected in a parallel arrangement. So basically, look at the guy on the left. He's sitting down, and the weight, gravity his weight is pushing down to the gravity, and A and B carries that. So that's a parallel arrangement. We'll talk more about this. It's with disjointed the way I'm presenting this. I find it funny. And we talk about axial loads here, so it's only axial loads to the center, arguably. And then in this case, on the right, we have a guy sitting, I don't know what that is, some type maybe, and he's applying a weight on that. But in this arrangement on the right, that each rope must carry the weight of the buoy. So the forces is shared, not shared, it's the whole weight is carried by each of those ropes. So when you're doing the analysis and when you're looking at it, this is what it's going to be, right? So in the series arrangement, the buoy on the right, each rope carries entire weight of the buoy in this configuration. So if one of the ropes fail, then the buoy will fall to the ground. So what we are saying, the total force is equal to FA equals FB. So it's rope A, rope B, it's all the same. Then I say the weight of the buoy will stretch the rope, right? Which means that the rope will stretch a certain length, and the sum of the total to change the length will equal the total change length. So therefore, we have to add each change length, which produces a total change length. The reason why I'm talking about forces, so we get to stresses. The reason why I'm talking about change in length, so we get to strains. It's not far from the concepts we've discussed so far. The one on the left, in parallel, where they're sharing the two ropes, so the two ropes each carry a portion. And of course, not 50-50. We don't know what it is. It could be 60-70, it could be 35-65, it could be any. Each rope carries a portion of the buoy's weight. The sum of forces upward must equal the weight downward. That's Newton's third law. And if one rope fails, the other rope might still be able to carry the buoy's weight. It's very interesting. Right? So you're building a structure. Think about these arrangements. This is analogous to having, if you have lights maybe, and normally we connect, lamps or lights, we connect them in parallel because if one circuit goes, we still have the other circuits. But however, if you have it in series, if something happens in that specific circuit, then all the lights, there's no current going through it, and all the lights won't work. And then again, at the same time, the weight of the buoy FT causes a certain stretch in each rope, and we assume that both change in length is exactly equal to each other. So we're saying that the strain will be exactly the same in both ropes. I hope that is clear to everyone what is a series and parallel, because we will be doing a lot of this. These kind of questions are also going to come in the exam, probably a series or a parallel arrangement. Right, there's some examples of shaft in series. Got your propeller shafts, essentially. You've got a propeller over there, that's for like a typical marine kind of thing. Here we've got the engine, clutch, your flywheel inside there, the essential transmission system, you've got a prop shaft, a differential, universal joint, and you've got a wheel. So it's like a deal shaft in series. In this case, we are looking at forces, but in the next subsequent chapter, we'll be looking at torques, which is more relevant to this kind of for that kind of analysis. But just to give you an idea that these things do exist, they're not just isolation. Right? parallel arrangement, it's not really common. Okay, so let's do this question. Right? I like you guys to try this question. So, first question, what arrangement do we have? And then I would like you guys to find the question and states that the extension of the bar, right? And I will do the next part again. So the first question is, what arrangement is this? Ms. Paulson, give me an answer. Didn't hear from you today. What arrangement is this? If she takes too long, someone else please respond. Tristan, Tommy, series, thank you. So the series arrangement, therefore, the force is the same in each member. And the change in length, we're going to have to add for each one. So the first question here is, what I'd like you guys to do is, I mean, what you should do is find the extension, because the other three here, is it the same? Yeah, on the other end, it's all the same. We've got some rod. Can we find the extension of the first section? So I'm going to recopy this question onto a whiteboard now. We can just play around. Would have normally done a smaller question on the slide itself, but it's okay. So I'm going to give you guys a chance, and we're using the same ideas of the previous section. So there's nothing new here. So remember here, we're looking for the total extension. We've got to add extension of the floor. We're going to call this maybe A. Can we call this A maybe? Call this guy B. We call this guy C. We call this guy E. We call this also A, B, C, D, and then E. And we're going to find the total. So if we had a bar and we're applying a load, whatever you need this bar, you're going to find that each part will extend individually, and each bar element carries the whole load. Right, so let's get the extension of section A. I'll give you 3 minutes to get that. Please put in the chat the answer in the chat, or you can shout it out loud once you find the first, just for the first section, and you guys can do the rest. I'll walk. I should be walking with you through this anyway. Just give it to me in the chat, or you can shout out. Anyone? The first section A, looking for the change in length. So, you slow today. What's happening? Sponges, get the first one. Do you guys remember there's like a short way to calculate this maybe? After Sitole, what sections A is changing length? Yes, all recordings will be on Blackboard. That is correct. Silas, you get the answer? Okay, so I'll start you guys off. I think people are rusty over here. So what you're going to have to do now is very simple. It's not that complicated. Or I shouldn't say that. Is you guys remember what's your change length equal to? So I'm just going to say A. I'm going to denote it as A. It could be called AB. It's fine. Just call it A. Is stress L over E. Alternatively, you can have it as F L E over A or flee. Right? So it depends on the way you want to work it out. Yeah, there we go. So I normally like to work out my stress first, and it's a specific reason. So let's quickly do that. Stress in the first section is going to be, the force is the same, so it's 800 power 3. And we've got 80 mil diameter there, right? So engineers, use engineering notation. Square that guy, get my stress value. My length is going to be 400 times 10 to the power negative 3. Of course, we can have it 0.4. And we've got our E, that's definitely a steel bar. And then what's that stress there? Okay, he's got an extension, or what am I doing? Sorry. 800 kilograms is a big amount. It's not a joke. It's not a joke. It's not a joke. My stress value is 159 point. Still within the elastic region, it seems. It's 55. You can go 49 if you want. So we go 159.1549. Okay, I'm running out of space here, but that's times 10 to the power negative 6. Negative 6. 6. My length is 400 millimeters. See, I'm fooling prey to habits here. It's 204, not 200. 204. Oh, you should get a small 3,12. No, there we go. Meters. Can you guys corroborate my answer? You guys agree that's for the first section, or you could say bar A, 3,12. My outside, maybe it's me. What's your stress value? Yeah, it's not. Yeah, 3, is it millimeters? No, it's not millimeters. It's 0,312. Right? Okay. We all get this answer. Let's look at that. That looks legit. Someone can just check, recheck again. Let's go to B. I expect the same. Can you guys give me for each section here? So we just have to find for A, B, and C, because we're going to get that. What is this? We're going to get that D and E is exactly the same as the other side again. So this is going to be exactly the same as section D. No, this is going to be section D. Sorry, E. And B will be exactly the same as. Okay, what's the next one? Can you guys get this quickly? What's the next one? Fitting. Definitely, I can zoom in. Sorry about that. It was a common problem. Yeah. I hope you can see it now. So once you find for each section, you're gonna have to add them up because it's a series arrangement. So always remember that. Series arrangement. So remember what arrangement you're dealing with. How is the load or the force going to be distributed? Okay, guys, taking a bit long here. So can I have a stress for section B? What's section B stress over there? It's 60 mole, right? 282. 942. Let's put that right. And I'm changing lengths. Someone figure that out. Thank you, Mr. Drill. Changing length. That's going to be 0.3. I'm not going to work out everything here. Just going to get the answers here. You guys agree with me? 4.1609 meters. Right. C, we're getting stress C here. And that guy is going to be, what's the guy going to be over here? C is at the big section. So by looking at this, this should have the least amount of stress. The highest should be the thinner section over here. So this is going to be power for what's the value? Shouldn't be writing this, but anyway, it's 100 more. So 0.1 squared. Yeah, so we all have 101.8. 8591, it's 856. Of course, we can get our extension here as well. So what's an extension over here? Let's see. Someone just get that for me. Okay, great. I'm happy with that answer. So we have 249.65. And of course, you have a small extension. If you look at the stress, it should make sense. And what we do now, we can tally, we can add up the total length, the total extension, we add up each of these. So we know A and E is the same. Oh, sorry, A and E and B and what's this thing called again? This is A same as E and this is the same as E. So we add them all up. So I'm going to say 3,12 times 10 to the negative 4 multiplied by 2 plus B is messy here. 4,1609 times 10 to the negative 4 times 2. And we're just adding up the small section here, 249.65. And your expected answer should be 1.708 millimeters. If you got that, well done. Fantastic. So Mr. Silva is our strength of materials expert over here. He's got a PhD in finite element analysis. We're expecting distinctions from him. All right, is everyone happy with this? Says please don't. Selling us up short. All right. So are we all happy with the total length? That looks legit. 1.7 odd millimeters. Small. You look at your vernier caliper, it's a small amount for that amount of load. Because you have a lot of elements here. Now, if you're all happy with this, I hope everyone's happy with this. My next question is now, right? Assuming the steel bar is made from ABS grade A, so all the grades over here, it's all the same. Determine which sections will fail. Assume failure, so should have been based, on the yield stress. So what I want you to do, you pull up a table, say 2 by 2 column, if you want, or maybe, yeah, so we can say for 3 columns, section, stress, and I'll say condition. Right, so we can just say, give me for my 4 lines here. It's going to be A, B, and C. And of course, A is the same as E, D is the same as, what's this? D. Right? Okay, this is supposed to be C over here. So when I talk about this concept of failure, right, this is what I mean. So the first thing is, look at the stress induced by this load, right? And then for the first one, this was 159. What was it? 154. I'll just call it 155. Of course, it's in megapascals. For B, got 282, 942. And then for C, we have 100 odd. Now remember what 100.86, let's say. So remember what I said is that if you're if your induced stress, right, is greater than the allowable or the yield in this case here. In this case, we're using yield as a failing criteria. Therefore, okay, let me just get this right. So we're going to say pass or okay. That means it's not going to fail. That's if your induced stress, which is this stress, is less than your allowable, or your yield in this case. And it fails, and when we mean fail, we mean it's going to break. Of course, our analysis currently doesn't tell us where exactly, but we have an idea. So if your induced is greater than your yield, what is going to happen? It's going to fail. Yeah. So if I look at section A, is this a pass or fail? Oh yes, and our yield stress for this grade is 235. So section AE, Mr. Silver, you got it to us? Is it going to pass or fail?
Section A, B will fail. It's 159.
Will fail. A, B, D, E will fail. No, that's incorrect. People are not getting the concept here. Who's not getting this concept here? So section A's induced stress is 159, right? That is less than the yield. Yes, Kaylin.
So the stress that we calculated, if that is
Yes.
less than the yield, then it won't fail.
That's correct. That's correct. That's correct.
Okay,
You
so
get
that
it?
means that if the, yeah, what did you say the yield stress was?
235 megapascals.
200. Okay, so then only B and D would fail.
That is fantastic. There we go. Who gets that? Who understands this concept of failure? This is how it works. Are we all happy with that idea of what's happening here? This is a very important concept because this is the practical significance of all of what we're doing. We're looking at when something's going to break. Yeah. Everyone happy with this concept? Because the idea is that when you buy the material, it comes with specific properties, right? And if we're going to load it up, and of course, there's different ways you can load the material. I don't want to go into the whole, explain all of that. But we're assuming we're loading up in a tensile force, there, tensile setup. What's going to happen is that, yes, that's correct, yeah, A and C. That if it's, as long as it's not, depending on what we can classify as failure, that's going to withstand the load. So you guys get the concept of failure and how the questions, always think about this. So you always know. Can everyone just give me a thumbs up if you're happy with this concept? So we can finally move on. So I'll sneak this question in. Guys, look at the end of the question of analysis. What's going to fail or pass? Let's see if you understand the strength of materials well. Can you get a few thumbs up? Is there a question there? Yes, Mr. Avano.
Yes, sir. Now I get it. BD will fail. I was just, yeah,
Yes.
was confused,
So
but
that
now
means,
it's okay. Yeah.
yeah, if we load this bar up, it's most likely going to either break at B or at D. The thinnest part, obviously, the thinnest section. And if you wonder why we manufacture our tensile specimens in a specific way, we have this reduced section, so we know that it's going to probably break on that reduced section. Okay, so guys, what we're going to do now, we're going to have let's have a break to 11:30, and then we'll proceed with our lecture. And then you'll probably I might go quite past lunch hopefully, but let's have a break to 30:30 and then proceed after that. Please. Yes, Mr. Silver.
So we don't have electrodes today. It's just strengths straight through into
Yeah,
electrodes.
Yeah, that's correct. Yeah, and then tomorrow we just have electrodes until we get the mom thing sorted out. Is that okay?
Okay. Yeah, that's fine. Can you tell me what you've covered in electro so far so I can just make sure I've covered it?
Yeah,
So
it's
that
on Blackboard.
I don't have access
uh,
yet.
yes, so it's chapter 1, and we started with chapter 2. So by
Okay.
tomorrow we'll be finished with chapter 2 basically.
Okay, cool, thanks.
Yeah, okay, great. So okay guys, I'll see you at 12:30. Make sure if you didn't eat something, make sure you eat. Because we have at least around 4 to 5 examples to cover. Or I think more actually. Yes, Brent?
Hi, sir. I don't know
Yes.
if I'm the only one facing this problem, but I genuinely cannot find the recordings of your past lectures. Someone was nice enough to
Yeah,
send me the link, but I cannot
yeah.
find the link itself.
Okay, so I've seen this like 1,000 times in the group already, but let me just start to show you
The
on my
the
end.
the student guide that you've sent, I've read it, and
Doesn't
in their
help.
pictures, they have a section to click on that I do not have.
Okay, so I'll stop that and I'll show you now. Let me just share. Where's Blackboard now? Just give me a second. It's confusing here for myself. I'm sharing my actual thing now. It's a bit weird. Let me just quickly see. Can you see what I'm seeing? No, it looks weird, right?
It's this mirror effect that's happening.
Yeah. So that's. So I'll speak to you. I'll speak to you. So that's snap, but I'll speak to you. After lecture. So what are you gonna do? Just quickly. Let me just stop the recording here.